So far, we've been taking a kind of bird's eye view of the periodic trends across the entire periodic table. Now we're going to zoom in a little bit into just group 1 to understand the trends for group 1 in a bit more detail. So let's get started. Our formal objectives are the following. I want you to be able to identify and explain the following trends for group 1 metals. They're melting and boiling point trends. These are their physical properties. And then for their chemical properties, they're reactivity trends with water, and you should be able to write the relevant equations, and with halogens, and of course you should be able to write the relevant equations there. Let's get started thinking about melting and boiling point trends. To understand the melting and boiling point trends, we want to recall our atomic radius trends. Atomic radius just means atomic size. We recall that as we go across a period, the atomic radius decreases. Why? Because we have the same number of shells. So here we have 2 shells, for example, in period 2, but the nuclear charge is increasing 3, 4, 5, 6. And so those protons in the nucleus here, those 6 protons, are pulling the electrons in tighter and tighter and tighter. And therefore, the atomic radius decreases across the period. Down the group, the atomic radius increases because the number of shells is increasing. So now that we understand the atomic radius, then we should be able to understand these melting and boiling point trends. I write that the trends in atomic radius are opposite, exactly opposite to trends in melting and boiling point for alkali metals. Okay? So here's a question for you. At room temperature, that's 20 degrees C, which alkali metals are gases, which are liquids, and which are solids? Pause the video and try to think through what the melting and boiling point mean, and therefore which would be gases, liquids, and solids. The way we'd go about this is you can think, well, let's take rubidium, for example. The temperature is increasing as we go this way, okay? And this is the, what? The melting point. So this is the melting point, 39, and this is the boiling point. So before 39 degrees, it must have been a solid. So we can indicate a solid like that. After 39 degrees, it becomes a liquid, so more spread out. And then after 688, then it's a gas, so extremely spread out. Okay, so 20 degrees, where is that? That is even before the melting point. So at 20 degrees, it is still indeed just a solid. At 39, it becomes a liquid. At 688, it becomes a gas. Hopefully that makes sense, pretty intuitive. And so based on this then, we can deduce that all of the alkali metals are solids at room temperature because for all of them, the melting point is above the room temperature value. Although if you go somewhere that's sufficiently hot, then you can get cesium and rubidium to melt at room temperature. In the middle of Texas, for example, this is probably going to melt, right? It's above 29 degrees C. On a regular hot day in Texas or in Lagos, where I'm from. Okay, so let's look now at these metals. So this is what lithium looks like. It's a shiny metal. It's fairly reactive, so we have to store it in oil. Same thing for sodium and potassium as well. Then we get extremely reactive as we go down to rubidium and cesium, and you have to store them in these inert, very delicate vials. And as you can see, it's really hard to get a large amount of them, so we only have pictures of really small quantities there. And you can remember the fact that the melting point reduces as we go down the group by thinking about how the texture of these. So this guy is fairly easy to cut. You can cut it with a knife, so it's about as hard as an almond to cut. But then as we get down to rubidium, it's extremely easy to cut. So it kind of has a texture of runny butter. It's so close to its melting point at room temperature that it's really easy to cut, very soft. Okay, so they get softer as you go down the group. And generally, group 1 metals are softer than other metals that you know of, like, I don't know, aluminum or gold. Okay? So now we understand that. Let's look now at how we can explain the boiling and the melting point trends. If we consider what it means for something to be a solid, a liquid, and a gas, when it's a solid, there must be some kind of force holding those atoms together for it to stay in this kind of nice lattice. Okay, and in a liquid as well, but slightly less. So I write that significant bonding force is needed to hold atoms together in a solid or in a liquid. Okay, let me get my mic out of the way. All right, and the strength of these bonds, therefore, determines a substance's melting and boiling point. I've got the apostrophe there, okay? So if you have a strong bonding force holding the solids together, then you need a lot of heat, a high temperature, to melt. So if you have a strong bonding force holding the particles together, then you have a high melting or boiling point. Okay? So the question therefore becomes, what bonds hold metal atoms together? And that would help us explain these trends. The bonds that hold metal atoms together are very appropriately called metallic bonds. So let's take a look at these metallic bonds and understand what they are. I say next that the trends in metallic bond strength will therefore determine trend in boiling and melting point. So what's a metallic bond? A metallic bond is the electrostatic interaction or attraction between a lattice of positive ions and delocalized electrons. Or you might hear a sea of delocalized electrons and a sea of delocalized electrons. Electrons are shared over many ions. What does that mean? Let's look at an example. Here we have lithium metal arranged as though it were in a solid. You remember lithium, you have 3 protons in its center and of course 3 electrons, right? 1 in that outer shell. It turns out that that outer shell or valence shell electron is not held on very tightly to the lithium atom. This is the case with all metals, right? Metals generally don't hold on too tight to their valence electrons. That's why they tend to lose those electrons to form cations. So that's exactly what happens when lithium is as a solid. It loses those electrons and they kind of just go around wandering anywhere, okay? So we have this sea of delocalized electrons. They aren't stuck to their respective atoms. They've left and are kind of cruising through the solid object. And so as a result then, what do we have? We have here a positively charged ion, a cation. Why? Because we still have the 3 protons inside the nucleus, but now we have just 2 electrons surrounding it. So we have a positively charged cation. And we have these electrons floating about. Right? And because of this, because of electrostatic interaction, right, if you have a positive charge and a negative charge, they attract each other by simple electrostatics, right? So now this object here is going to be attracted to that negatively charged thing. This ion is also attracted to it. This ion is also attracted to it, and this ion is attracted to it. That one is attracted to that guy and that guy. And so they're all kind of attracted to this sea of delocalized electrons. And in the process, they're stuck together. It's a kind of bond. It's a metallic bond. Consider an analogy here. We have these octopuses, right? And they have these 2 eggs. The eggs are their inner shell electrons. Okay? But they also have outer shell eggs, but they tend to lose those eggs. Okay? So after losing the eggs, this guy says, oh no, I lost my valence egg again. That must be mine. So he's looking at this valence egg and saying, oh, that one must be mine. This guy says, no, I'm pretty sure that one is mine. This guy says, no, that one is mine. And then he's also fighting with this guy for this one. So because they're all fighting for the same electrons, even though they lost the electrons in the first place, so it's like, why do you lose the electrons in the first place if you still want to hold on to them? Huh? Silly metallic bonds. But anyways, they're all holding on to the same electrons, and therefore they're stuck to each other, forming therefore a solid or a liquid if you raise the temperature enough. Okay? So now back to our question, how do we explain the boiling and melting point trends? By differences in metallic bond strength. So as this bond here that we've described, this metallic bond, as that bond strength changes, the melting and boiling point will change. So let's look then at this concept. To do this, I'm going to change the representation of the lithium metal to something like that, because it'll be easier to explain what I need to. So again, we haven't changed much. All that we're saying here is that we have a positively charged cation, right? And of course, this positively charged cation will be attracted to the sea of delocalized electrons. So we have that kind of mutual attraction there. Now consider how this here, lithium, would look different from, say, potassium. That's what potassium would look like. So it's a similar situation. Potassium would have lost this outer shell electron. And so this inner thing here would now become a positively charged body, a cation. But in this case, look how big that positive charge is. Look how big the amount of space that the positive charge needs to spread itself over is. Okay, I didn't say that properly. Look how large the space over which the positive charge is spread is. Okay, all right. Let me look at my my slides. Here we have fewer shells. Okay, so just one shell in this case for this ion. And that leads us to a smaller radius, a smaller size, which means we have a higher charge density. This is the word I think I was looking for, a higher charge density, because we have here a single charge spread out over a small space. And because we have a higher charge density, the metallic bond strength is more. So the ability of this positive charge to hold on to the free electrons is more here relative to here. Here we have a positive charge and it's spread out thinly over this large space. So this guy has to reach all the way over there, right? Or over the way over there, okay, to hold on to these electrons. So that here at the top, then we have a higher metallic bond strength, which means a higher melting and boiling point, because we need to put in more energy to break these bonds, these metallic bonds. Okay, and the reverse would be the case there for potassium. We have more shells, which gives us a larger radius, a lower charge density, that is, the charge is spread out over a larger space, and therefore a lower metallic bond strength. And finally, we end up with a lower melting and boiling point. If we go back to our analogy, the analogy starts to break down a little bit here, but you can think this is the situation with lithium. They're all basically able to hold on to their electrons with a decent amount of vigor. Whereas when we skip over to potassium there, because potassium already has these 18 electrons, the 18 inner shell electrons to guard over, then they're a bit tired. They can't really hold on to these free electrons too tightly. So this guy says, oh, I believe that egg is mine. And he says, I think it's mine too, but I can't really reach that far. And he says, oh, I guess it might be mine. And he's like, is it mine? So they're not holding on to it too tightly. And therefore, if you add any decent amount of temperature, then these atoms will break apart and you end up with a liquid or a gas. The melting and boiling points are in your data booklet. So in section 7 here, at the top of each cell, you have the melting points in degrees C, and at the bottom, you have the boiling point in degrees C as well. Okay, so if you forget any of the trends, you can come over here and look at them. Here is the 3D representation of this table here, showing you the melting points in degrees Celsius of each of the elements. And we can see, if we zoom in on group 1, the alkali metals, we can see there is indeed a reduction in melting point as we go down the table or down the group. Okay, and for boiling point, we see a similar thing, a reduction in boiling point as we go down the group. We notice that generally speaking, the alkali metals melt at much lower temperatures than the other metals, specifically the transition metals there. You can see tungsten melts at a very high temperature. Okay. All right, so now I think we can explain the melting and boiling point trends for the alkali metals or the group 1 metals. Let's look at some questions. This one asks, which of the following is true of the melting points of rubidium and lithium? As always, pause the video and read through the options. In 2 seconds, I reveal a clue, 1, 2, and a clue. If you need to pause again, pause again. In 2 seconds, I reveal the answer, 1 and a 2, and the answer is C. Okay, so you should have been able to deduce from this guy here that rubidium melts at a lower temperature than does lithium. So you can easily cross out those two. Okay, so you'd have access to this on the exam, and you can deduce that fact. Okay. Now the question is, does it have a weaker or a stronger metallic bond than lithium? And if we look at this picture, we should recall that smaller ions will have stronger metallic bonds because they're better able to reach across to attract those free electrons. Whereas here, we have a large ion, therefore the ability to reach across, or more formally, the charge density is reduced. So the actual, the pull, the mutual pull on these free electrons is reduced in the large atoms. So we end up with a weaker metallic bond in the larger rubidium. Okay, so there's a C for the answer. Here's another one for you. Which of these best accounts for the decrease in boiling point down group 1? Again, pause the video, think about how you'd answer this one. In some seconds, I show you a clue, 1, 2, and a clue. Some seconds, I show you the answer. Pause if you need to, 1, 2, and the answer is A. Okay, so all the other ones here are actually correct statements. They're all correct statements, but only A explains the trend. So let's look at the other statements. This one says, the nuclear charge increases down group 1. Yes, the nuclear charge increases down group 1, but that doesn't explain our trend because in the end, we're still dealing with a singly positive ion. So this is just an ion with a +1 charge. This is an ion with a +1 charge. So we don't care too much about the overall nuclear charge. Or, I mean, we don't care too much about just the nuclear charge. What we care about is the overall charge of the ion, right? The mass number does increase, but I mean, who cares about that here? The neutron number increases, yes, but completely unrelated, okay? So of course, it's because the ionic radius is increasing. So here we have a larger ion, which leads to a lower charge density, okay? You can think of the octopi are stretched out, and so they can't, or did I say octopi? I think it's octopuses, right? The octopuses are stretched out, and so they can't reach to grab those free electrons. Okay, I think now we get a green light with melting and boiling point trends. Let's move to chemical properties, the reactivity trends. Okay? Here's a statement for you. Alkali metals displace hydrogen from water to form alkalis. Okay? So remember what we're trying to explain are the reactivity trends of alkali metals with water. And it turns out that they displace hydrogen from water to form alkalis. That's why they get the name alkali metals. Because when they react with water, like sodium, they're reacting with water, they form an alkali. What's an alkali? Alkali is a base. And the reason this water is turning purple here is because we put a kind of indicator in it that turns purple when the solution is basic, when the pH is above 7. Okay? Now let's see if we can look at what this reaction looks like in terms of the interaction between the different atoms and molecules. So let's look at lithium. So we take a lithium atom and we try to react it with water. Hopefully you know that this is what water looks like, right? So H2O, which is just two H's, and one oxygen, right? And it has this Mickey Mouse shape for reasons maybe we will discuss in another video. So I'm just going to copy the reactants and put them on the product side, and we will manipulate the products over there. So here's the reaction between lithium and water. That's the reaction, okay? So it's a very simple reaction. Simply speaking, like I said here, the alkali metal has displaced hydrogen. So the alkali metal pushed out hydrogen from water to form an alkali. What is this guy here? That's an alkali, lithium hydroxide, okay? And conventionally, we put the lithium hydroxide first. So let's see now how we would write this as an equation. So we have lithium there, plus, for now we just write HOH, that's H2O, gives you lithium hydroxide, LiOH, plus a free hydrogen atom there. Okay? But here's the kicker though, or here's the problem rather. Hydrogen is a diatomic molecule. So whenever you have one hydrogen, you're going to have a second hydrogen. So we need to figure out a way to put H2 here, because H doesn't exist on its own usually. Okay? And so when we put the second H, we then tell the story of the other set, or of the other hydrogen. So this hydrogen was displaced from this guy when this hydrogen was displaced from this water molecule when this guy kicked him out. And that hydrogen was displaced from this water molecule when that guy kicked him out. Okay? So now we end up with the H2 there. And how would we write that as an equation? Let's see. So we have H2, and then we double that one. So we have 2 LiOH, 2 HOH, and 2 Li. And if we put it in a more formal form now, we have 2 Li atoms, and lithium is solid at room temperature. You should remember this. Then 2 H2O, liquid at room temperature. 2 LiOH, that's aqueous, right? Because it's dissolved in water. This reaction is taking place in water, obviously, because we put the lithium in water. Okay, and we have H2, which is a colorless gas. So those are that's the reaction of lithium with water. Now we can just replace lithium with any of the other alkali metals, and the reaction looks exactly the same. We just change out the red guy. So we have sodium there, potassium, rubidium, and cesium. And what is the trend of reactivity? Well, the trend of reactivity follows the trend of reactivity for the alkali metals generally. So generally, hopefully you remember this, cesium would be the most reactive in this list here, and lithium will be the least reactive. So reactivity increases down a group, and therefore reactivity with water also increases down a group. And we can look at some very quick GIFs of the reactions of these respective metals with water. There's lithium with water. There's sodium with water, which we've seen before. You can see it, if you get enough sodium, you get a tiny explosion. There is potassium with water, big explosion from the guys at Periodic Videos, good YouTube channel. And then from Brainiac there we have rubidium and water. And you can imagine what cesium and water looks like. There are no good videos of that one. So now we have an orange light with being able to explain the reaction with water, the reaction between alkali metals and water. Okay, and hopefully you can write any of those equations that you were asked to write. It's the same thing for all of them. You just switch out the different metals. Let's try some questions. Which of these occurs when potassium is added to pure distilled water? Pause the video if you need to. Think about this. Rewind the video if you need to. In 2 seconds, I show you a clue 1, 2, and a clue. There's our clue there. There's a reaction with sodium, but it should be the same for potassium. Okay. Pause again and think about it. Our answer is D. Okay, so they're all correct. So a colorless gas is evolved. Yes, that's the hydrogen gas. You don't see it there, but it's there. So it's colorless. A colorless alkaline solution is formed. Yes, sodium hydroxide is colorless. The reason where it's turning purple here is because we have that indicator that's making it purple. But naturally, sodium hydroxide, lithium hydroxide, all the hydroxides for the first, I think all hydroxides are colorless. But don't quote me on that. And then heat, of course, is given off, as you can see, from that exothermic reaction. Here's the last one for you. Which of the following would react most vigorously with water? Pause the video as always, think about it. In 2 seconds, I show you a clue, 1, and a 2, and a clue. In 2 seconds, I show the answer, 1, 2, and the answer is B. So cesium is the most reactive because reactivity increases as we go down the group. Hopefully you remember why that is, because these guys are basically least able to hold on to their electrons. The electron is getting further and further away from them, and so they lose the electrons very easily, and so reactivity increases down that group, making cesium the most reactive. Below cesium is francium, but I've cut that out because I didn't want to have to do so many electrons. This got very hard to make. So now hopefully we can identify and explain the reactivity trends of alkali metals and water, and we can write the needed equations. Let's look now at the reactions with halogens and try to understand those equations as well. So if you take an alkali metal and you react it with the halogen, you're going to get a very highly exothermic reaction. Why? Because alkali metals and halogens, we can think they love each other so much. Let's see why they love each other. So remember that we said that the ionization energies for metals are very low. For alkali metals, the alkali metals have the lowest ionization energies, which means that very little energy is needed to remove their electrons. So very little energy is needed to remove the first electron of sodium, for example, or cesium or francium. And on the other hand, if we look at the electron affinities, we see that halogens have the most exothermic electron affinity. That means lots of energy is lots of energy is given out when they capture an electron. So if an electron falls into, say, fluorine here or chlorine, it's going to release lots of energy. And so because we need a very low energy investments to take off an electron from these guys, and we release lots of energy when we drop them in here, then the overall reaction will be exothermic. It'll release lots of energy, right? Imagine if you had to take an electron from, say bromine and drop it into fluorine. You need lots of energy to remove the electron from bromine. And you get lots of energy when you drop it in fluorine, but because you needed a high investment, the net energy change will be quite low. And for that reason, that reaction doesn't go too fast, or maybe it doesn't go at all. Okay? So here you need very little energy to take off the electrons. We can think about it also in terms of this schematic I've given you, where you think that they're all trying to attain a noble gas configuration. Okay? So if we look at the electronic structure of lithium and chlorine here we have lithium, and there we have chlorine. Okay? And remember that we said that electronic behavior equals what is the shortest path to the throne, or to a noble gas configuration. What is chlorine's shortest path to the throne? Chlorine can gain an electron and look like argon, and they'll be very happy. Okay? And lithium here can lose an electron to look like helium, and we can think it'll be very happy. So these guys then, and those guys, 17, are very happy together because these lose an electron and those would gain that electron. Okay, that's one way to think about it. But the more accurate way is in terms of ionization energy and electron affinity. But the easier way is just to think these like to give away electrons and those like to take electrons. If you're being more accurate, you realize that they don't really like to give away the electrons. It's just that it doesn't take too much energy to take the electrons away from them. They don't actively throw away the electrons the way this analogy would make you think. But anyways, we use the analogy. So we take lithium and we want to react it with chlorine. I'm going to duplicate these guys on the other end. Before that, let's change their colors. Okay, now we duplicate them on that end and we can watch the reaction go on the product side. So here's the reaction between lithium and chlorine, ladies and gentlemen. There's your reaction. What a beautiful reaction. Okay, so an electron has been transferred from lithium to chlorine. And you notice now they're both happy. So that outside shell of lithium has disappeared then. And lithium now looks like helium, so we can think it's happy, it has attained its noble gas configuration. And chlorine looks like argon, so it's happy as well. And now lithium is positively charged, right? Because now we have 3 protons and only 2 electrons. And chlorine is going to be negatively charged because we still have those 17 protons in here and we gained an extra electron. And what happens between positively charged and negatively charged things? Electrostatic attraction. So they pull against each other and then we form we can think a lithium chloride molecule. Although we don't really talk about lithium chloride molecules. We'll talk about why in a future chapter. Anyways, you can think of this for now as a molecule. We have LiCl solid, and we started with the lithium solid plus chlorine gas. Of course, we're not quite done. Why? Because this thing that we put here, it doesn't tend to exist on its own. So chlorine is diatomic, which means when you have one chlorine here, I moved the gap from here to here. But anyways, we have one chlorine. Generally speaking, it'll be attached to some other chlorine. So those two will be attached together in a covalent bond. So they're sharing electrons here. And so they're kind of both getting to be kings. They're kind of both getting to be argon because they sort of both have full shells. But it's not as good as they would like. They'd like to have a real full shell by just taking these electrons. So now let's duplicate the lithium and then put that on that side. And we can watch the reaction go there. Again, it's the exact same reaction. So now the chlorine will break up into the separate chlorines and then just take the outer shell electron, the valence shell electrons from lithium. And then we have the same thing. We have those cations there, those anions. They attract each other. And now we can write down a more accurate reaction. So here's our final reaction. Then we have 2 lithium solid atoms, all right, plus a single chlorine molecule, gaseous, gives you lithium chloride solid, 2 lithium chloride solid molecules. Okay, so hopefully now, after looking at these pictures, you should be able to write out the reaction of lithium with chlorine with the right state symbols and balancing and all of that. What is the trend? The trend, of course, is that it gets more reactive as we go downwards. The same thing with the water. Okay, so this guy is more reactive than that guy, and therefore we should have a similar situation there for the reactivity with halogens. And the equations look more or less the same. So there's lithium there with chlorine, and then sodium with chlorine is the same. You just switch out the alkali metal, and potassium, rubidium, and cesium. Now, if we chose to react these instead of with chlorine, and we chose to react them with, say, fluorine, which is even more reactive than chlorine with the alkali metals, then we would have, the trend would stay the same, but overall, each of them would be more reactive than with just chlorine. Okay. So in a future video, we'll talk about the group 17 element, and we will look at that in a bit more detail. Okay. For now, let's watch a quick video of this reaction here. Sodium and chlorine forming what? Sodium chloride, which is, of course, one of the most common molecules that you're familiar with. Okay. So we look at this guy, Nayared, very good YouTube channel, highly recommend for chemistry videos. Okay, and he's going to react sodium, solid sodium metal, with chlorine gas. So let's watch that. So he takes that heated up sodium metal and he puts it in this Erlenmeyer flask that has chlorine gas in it. And what's going on in there? What's going on in there is that electrons are leaving sodium and falling into chlorine and releasing lots of energy as they fall into chlorine. And we're going to end up with sodium chloride gas. Sorry, sodium chloride solid. Okay, so there's our sodium chloride solid table salt, which if he chose, he could put on his food and consume. And if you want, you could look at some even more exciting reactions. Here's the reaction with fluorine and cesium. I won't play this one, but they get exciting. People love reacting the group 1 metals with the halogens, because those are the sort of the two most reactive groups. And so you can get really exciting reactions when you do those. So if you like, you can scour YouTube for such videos. Okay, now we have an orange light for the reactions between group 1 metals and the halogens and the relevant equations. Let's try and get our green lights by answering these questions correctly. Which of the following is the correct equation for the reaction between sodium and fluorine? As always, pause the video, read through the options, think about how you would answer it. In 2 seconds, I show you a clue. 1, 2, and a clue. What happened? Where's the clue? There's the clue. In 2 seconds, I reveal the answer. 1, 2, and there's our answer. B. Okay, so let's think about why the other ones are wrong. So here we have sodium reacting with fluorine, but then we have a single fluorine atom, which is no good, because fluorine doesn't exist alone like that. And it's solid, oh, I don't know why it's solid. And then it becomes aqueous. Oh, this is just a whole load of bollocks, that one. C, here we have Na2, and that's wrong, that doesn't exist. This guy, 2F, doesn't really exist. This is correct, but that's the only correct thing. And then this is the reaction for potassium. Okay, so if you use this, then you need to go back to if you pick this one, you need to go back to elementary school, because you don't know how to answer multiple choice questions. Okay, so this one must be the answer then, B. Okay. When I say you don't know how to answer multiple choice questions, I mean if you have 3 A, B, C, and they all start with Na, Na, the chances there's going to be this one that just starts with K is usually low. Right? That's not how multiple choice questions typically go. Okay, we look at one last question. Which of the following reactions would be the most exothermic? Pause the video, look at the options, think about it. In 2 seconds, I show you a clue. 1, 2, and a clue. No, there's a clue there. 1, 2, I show you the answer. 1, 2, and D. So rubidium is the most reactive of all of these, because reactivity generally increases as we go down the group. Okay? So rubidium is more reactive than potassium, and so on and so forth. Okay, I think now we are done with our final objective. We understand the reactivity trends with halogens, we can write the relevant equations, and therefore we are done with this video. So I wish you good luck and happy practicing. Bye-bye.